Inverters. What are they and what do they do, and why might you want one? In short, they turn battery DC power into household or domestic AC power via a physical hardware device. Inverters come in varying different power ratings that are usually based on the amount of AC power that they can output. This AC output figure is usually represented in watts and may be part of the product identity or model description. For example, Lil 1000 inverter or the MacDaddy 5000 watt inverter, and so on. So, let me explain this a little more clearly. You may have a leisure battery or bank of leisure batteries. The battery or battery bank could be wired in a configuration supplying 12, 24 or 48 volts, or possibly even more volts. The most common inverter input voltage being a nominal 12 volts, nominal meaning roughly or in the vicinity of. However, just be sure to check the voltage that your leisure battery system is configured at and what voltage the inverter you're acquiring requires. The voltages really do need to match. An inverter will convert the power from your DC leisure battery or batteries into AC electric power, just like the AC electric power that comes from a domestic household wall socket outlet. Please see my number 2 AC Electric Basics tutorial for a better understanding of AC electricity. As well as the voltage, an inverter's rated wattage is something you should pay close attention to when figuring out which inverter rate you really want or need. When purchasing or acquiring an inverter, be careful of the wattage stated on the case or the box. Some inverter manufacturers or retailers like to state the surge or peak power wattage rather than the continuous rate wattage. Realistically, you want to base your needs on the continuous rate wattage, not the surge or peak power wattage. Advertising an inverter's surge or peak power wattage is often just a marketing ploy. What you really need to know is the inverter's continuous rate wattage to make a realistic purchase decision that has a better chance of covering your needs. Surge wattage, or the peak power wattage, is the absolute maximum power that an inverter can supply, but only for a short time, like a few seconds. However, on some models it can be as much as a few minutes or so. Also, the surge or the peak power wattage can be at a rate that might even be more than double the inverter's realistic continuous rate, so be mindful of these figures. All inverters will have to display somewhere their continuous rate wattage. It's the continuous rate wattage, or words to that effect, that we need to base our calculations on. Just to explain what surge wattage or the peak power wattage is, some appliances, particularly those with electric motors, need an initial boost of electric power in order to get started. That boost of electric tends to drop back down to its regular stated continuous power consumption as soon as the appliance gets running steadily. So, most inverters have a surge factor built into them to compensate for this initial guzzle of electric power that is required by some electrical devices to get started. That surge often being created by anything with an electric motor in it that just needs that extra boost of power or an electrical kick in the pants to get it started. Like for instance, a refrigerator's compressor, if that is, it's a compressor type of a refrigerator. For the first moment a refrigerator's motorized compressor cycles on, it needs just that extra boost of power. Then the compressor will settle down into its regular power cycle, and its initial power consumption will drop back down to its regular rate, that being when the refrigerator's compressor gets its cycle properly started. As it is, fitting an inverter into your system can be a bit of a balancing act, but very doable. Have you got enough DC power stored in your batteries or coming into your system from your alternative power sources to power what will be getting consumed in the way of AC power being used by your domestic type devices? Firstly, there are generally two different AC or household voltage rates being used domestically throughout the world. Again, please see my number 2 Electric Basics tutorial for a better idea of what you might be dealing with voltage wise. It's as easy as pie if you have a basic understanding of what you're cooking with. There is the US standard voltage, or what I call the American voltage, which is also used in a few other countries outside of the American continent, that being 120 volt at 60 Hz. And then there is the EU, UK, New Zealand and Australia and other countries standard voltage. I like to call this the Commonwealth voltage of 230 volts at 50 Hz. There are a few other countries with odd and different voltages, but we won't worry about them for now. Again, please watch my number 2 AC Electric Basics tutorial for more on AC voltages and what the Hertz or Hertz factor is. Okay, so you might need to do a wattage audit of all the regular AC household devices that you might be wanting to use simultaneously and try to come up with a sum total wattage figure. Every AC device will have a label stating what its running wattage is, usually not taking into account its startup or surge wattage, but that's okay. In respects to buying an inverter, it's always better to go a little higher in its continuous rate wattage than you think you might need. Keep in mind future growth. It may be possible that in the future you will need more AC power, so you might need to upgrade your inverter or add another inverter wired in parallel, if that is your inverter model supports multiple inverters being connected together. Please read the inverter manufacturer's documentation or make inquiries to see if your inverter supports multiple inverters being connected in parallel. Some inverters can be wired together to upgrade their wattage. However, they usually need to be identical inverters, identical manufacturer, and identical in wattage. Naturally, you would also need to upscale your battery bank and your wiring gauges to accommodate the extra DC power demands being made by this kind of upgrade. But that's a future issue, just something to keep in mind if you think you might want to upgrade that way in the future. Sometimes, if you know you're going to upgrade and add an inverter in the future, it's best to overgauge the DC wiring the first time around. Oversized DC wiring won't cause any problems, just heavier gauge wiring costs more, but you might save yourself the headache of rewiring and having to buy thicker, heavier gauge wiring in the future if you plan your wiring ahead. For the scope of this tutorial, I'm going to use an example 1000 continuous rate watt 12 volt inverter with a peak surge rate of 2400 watts and a 12 volt 100 amp lithium ion or LiFePO4 leisure battery in a fairly basic setup. For this tutorial example, I'm looking to charge up a couple of electric bikes in a motorhome via their manufacturer supplied AC power transformer blocks. Those power blocks being AC transformer blocks that would come with the e-bikes and that you would normally plug into a household electric power outlet. Please note, it's sensible not to try and use an inverter running solely from an off-grid power source like solar panels or a wind turbine or a vehicle or boat engine alternator. It's always best to have some kind of battery or batteries as an intermediary power source, as an inverter works better with a fairly stable DC power input. So, if there is a drop in the DC input power, like a cloud passing over the solar panels, or an ebb in the wind pushing the wind turbines, then an intermediary power source like a leisure battery will compensate for that momentary drop in power and maintain a consistent and stable flow of DC power to the inverter. Another term that you will often see related to inverters is pure sine wave or modified sine wave. So what do these terms mean exactly? If you want a more in-depth description of what a sine wave is, please see my number 2 AC electricity basics tutorial. In short, AC electricity modulates. That is, it swings from one polarity to another polarity. Stay with me. 50 or 60 times a second, sometimes referred to as Hz or hertz per second, like positive to negative and back again on the same single wire. That's right, one cable or wire being both positive for a split second and then negative for a split second. That one AC wire being both positive and negative 50 or 60 times a second. This single AC wire colour usually being brown in the EU and UK and black in the USA. AC electric power being somewhat like a compass needle spinning around and around a compass face, pointing at north, then south, then north, then south, or positive, then negative, then positive, then negative, 50 or 60 times a second. Those cycles of the spinning needle per second being called hertz and are relative to whatever country electric system you might be using, such as 50 hertz or Hz in the EU or UK and some other countries like India, Australia, New Zealand and other Commonwealth countries, and 60 hertz in the USA and some other countries on the American continent, and even countries beyond the American continent. It tends to be wherever 230 volts is used, it cycles at 50 hertz, and wherever 120 volts is used, it cycles at 60 hertz. Not a hard and fast rule, but it seems to be more often than not the rule. It will usually mention the hertz, often abbreviated down to the letters Hz, on the equipment manufacturer's label. It's not just the voltages that are different in these differing countries, but more often than not, if you buy your equipment at the right voltage in the beginning, then the hertz will already be matched up. So don't be intimidated by the hertz thing, but I thought I'd just explain it so you know what it is. However, something to keep in mind using the compass example is that the spinning compass needle will travel all the way around the compass face. As it approaches north, it gains strength, and as it passes by north, its strength ebbs off. Then it approaches south, it gradually gains strength again, and as it passes by the south, its strength ebbs away again. It's this smooth, gradual gaining and ebbing of strength or polarity that can be referred to as a pure sine wave. It's kind of like a smooth, throbbing transition from positive to negative and back to positive on the live AC wire, which again is the brown wire in the UK and black wire in the USA, through whatever electrical device you are trying to operate, assuming the device is turned on, and then the throbbing AC power returns back down the blue neutral wire in the UK or the white neutral wire in the USA, still throbbing away at 50 or 60 hertz a second, north and south, or positive and negative, and not positive and negative to whatever the power initially came from, in our case the inverter. That's basically the difference between AC and DC electricity. It's the hertz throb in AC electricity that is used to power AC power devices and make them do what they're made to do, whereas in DC electricity is the push and the pressure of the power down the wire, and it's one-way force and push of the electricity that powers DC devices, making them do what they were made to do. The other inverter type is what is called a modified sine wave inverter, which uses a rough rather than a smooth transition of polarities. It has a rather abrupt and instant switch from one polarity to the other, not smooth like the pure sine wave inverter. A modified sine wave inverter is like north-south, 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 without anything in the way of a smooth and gradual transition in between its cycles. Just an abrupt instant change of polarity, back and forth, north-south, 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 positive, negative, positive, negative, positive, negative, going down the same brown wire in the UK, or black wire in the USA, and returning, if it can, on the blue wire in the UK, or the white wire in the USA. The modified sine wave just jumps directly from one pole to the other. No smooth, easy transition, like the spinning of a compass needle. Just bam, 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 north-south, 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 like a switch being thrown back and forth. No gradual or nice, smooth, easy transition from the north to the south pole. Just a hard, abrupt switching of north-south, positive, negative, 50 to 60 times a second. A lot of electrical devices don't really like this abrupt sine wave change in polarity. It's too harsh for them. So people pay a little extra money for the pure sine wave inverter that has a much nicer and smoother polarity transition, be that at 50 or 60 times a second. Pure sine wave is just better for most things than the modified sine wave. Think of it this way. Pure sine wave is much better for using with sensitive AC electronic devices, like computers and TVs and the like. If you just want to run an electric drill or an electric kettle or hairdryer or something like that, then a modified sine wave inverter will probably be adequate. However, if you're considering using anything more sensitive like a TV or a computer or anything with microelectronic built in, then you'll probably be better off by choosing the pure sine wave inverter. A pure sine wave inverter is also more efficient as it has less in the way of power overheads in its DC to AC conversion. However, please note that pure sine wave inverters do tend to cost more. Also, just in case you're wondering, a pure sine wave inverter will run an electric drill or an electric kettle or a hairdryer just as well as a modified sine wave inverter. However, a modified sine wave inverter might not be able to run some computers or TVs or any number of other sensitive electronic devices. So in short, pure sine wave inverters will cover most all of your electrical power needs. However, modified sine wave inverters can be somewhat limited but might power basic appliances. So what other important factors do we need to take into account when purchasing or acquiring an inverter? Idle consumption, sometimes called no-load current draw, or words to that effect, is an overhead or tax made on your leisure battery or batteries by the inverter, even whilst it's not being used to power any AC devices. However, the inverter is still powered on, so it still sucks some electricity out of your DC battery. Sometimes not much, but still something that might add up if left on for an extended period. Something to look for on an inverter is there being an easy way to turn off your inverter when it's not in use. Some inverters allow a Bluetooth phone app to remotely control them, turning them on or off if and when needed. Some inverters have a power saving feature, that is, when there is no AC demand being made on the inverter, they go on a sort of low idle power saving mode. But again, it's still power you'd rather not lose if possible. If you're say running an AC refrigerator and have to keep the inverter turned on, then the power saving mode might help save some power between refrigerator compressor cycles, but that's about it. Or the inverter might facilitate the wiring up of a remote switch. If that is, the physical inverter has been placed in a difficult to access location and the power switch on its casing cannot be accessed. A remote on-off switch may be located somewhere a little more convenient to access and can be used to shut the inverter on and off manually as and when needed. In short, are you going to be able to harness enough DC input power by whatever means, like solar, wind turbine or vehicle alternator, to keep your battery or battery bank charged up with enough DC electricity held in reserve for powering other DC power requirements like lights, phone chargers, 12-volt refrigerators, and enough extra power to be converted into AC electricity for devices that require a domestic 120 or 230 volt of AC electricity? Therein lies the question. It's not as easy as just going out and buying the biggest inverter unit that you can afford, although you can buy and fit an oversized inverter than your present ability to supply DC battery power to might be for that particular inverter to run at its maximum power wattage. That being, if maybe you are planning on upgrading your battery or battery bank later down the road. However, something important to keep in mind is, if you have your inverter turned on, however nothing is actually utilizing any of the AC power the inverter is creating, the inverter will still be taxing your battery or batteries of some of their stored power. Again, it's called an idle consumption load, or sometimes called a no-load current draw, which effectively, all but maybe slowly, will drain your battery or batteries batteries, whilst the inverter is not actually even supplying any AC electricity to anything. The larger the wattage rate of the inverter, the higher the drain it will put on the battery or batteries in the way of idle consumption or no load current draw. Again, regardless of whether it is actually being used to supply AC power or not, as long as it's turned on, it's using some DC battery electricity. So keep that in mind. Be sure to turn the inverter off when not in use. However, people often do forget to turn their inverters off and find their leisure batteries run down and don't seem to know why. I will say that it's something of a balancing act getting the right inverter, but with this tutorial you have a fair chance of getting something that will suit your needs. Here are a few other things that you might want to take into account. Can you afford to run very power-hungry AC devices on the DC leisure battery power that you presently have? And what replenishing DC battery charging power can you realistically generate to recharge your batteries if they should get run down? Basically, you need to figure out roughly how much AC electricity you might want to use, or how much AC power you might use at any one time collectively at its maximum draw. This might require evaluating or guesstimating the power draw of all the AC devices that you might want to possibly run simultaneously or simultaneously, and for how long you might want to run those devices for. Wattage figures are usually supplied on most AC electric device manufacturers' labels. Basically, as I said earlier, you might want to do something of an audit of your domestic device wattages and come up with a combined total wattage as a sort of potential worst case scenario figure. Don't worry, it's not all that complicated. Once you get a grasp of what goes out of your battery also has to come into the battery, kind of like a bank account, only you're putting one currency in, the DC power, and taking another currency out, AC power, and unfortunately you have to pay a conversion fee for facilitating the exchange. Let's break down how we can calculate this, that being the DC to AC figures. Again, it's not really that difficult once you grasp the basics. In this example, I'm going to look to charge up 2 electric e-bikes that use an intermediary AC transformer charging block, like what we might use in a regular building. We need to look for a label on the charging blocks that gives us the wattage at maximum draw. As it is, both the charging blocks indicate that they will charge the bicycles at a rate of 48 volts at 6 amps maximum, which calculates to 288 watts each charger running at maximum charge. That's 6 times 48 equals 288. Please see my number 3 electric basics tutorial for more on watts and wattage and how these figures are arrived at. Basically, it's just a calculation of one aspect of the electricity times the other. Volts times amps, or amps times volts, equals watts. In this case, we came up with 288 watts. That is 6 times 48, or 6 amps times 48 volts, giving us 288 watts. Often, the device will have its maximum wattage rate stated on its label. So, we know from the power block labels that we will need a minimum of 288 watts for each e-bike's charging block. So 2 of these AC charging blocks being plugged into the AC side of the inverter at the same time would equal 576 watts drain on the DC leisure battery. To that figure, we should add an overhead or an inverter running tax, depending on the quality of your inverter, normally about 10% or a little less. Some inverters are very efficient and might use less than 10% added onto the supplied DC electricity. However, there are some out there that are not so efficient, so I would use a 10% overhead as a good rule of thumb. Another way the overhead might be referenced or termed in the documentation is as an efficiency rating. The manufacturer might call it a 10% overhead or a 90% efficiency rating, one or the other. The 10% rule of thumb is not a carved in stone overhead rate, but certainly a rate worth using for generalized calculations. Basically, whatever you're pulling from the DC battery in the way of wattage into the inverter, you need to add an additional 10% to, which would bring us to, if we were to max out the entire 1000 watts of 230 AC power, or 230 volts of AC power from the inverter, the DC power draw on the leisure battery side would be roughly 1100 watts. This shouldn't be a problem for my 12 volt 100 amp hour lithium ion battery, as it should give me at least 12 to 1320 watts if fully charged for just over an hour, if being discharged, that is, at 1100 watt rate. Don't forget the battery to inverter cable wires must also be adequate enough in gauge and thickness to handle this much DC electricity flow. Please see my number 5 electrical wiring tutorial. Incidentally, discharging a battery at its full stated rate would be referenced as a 1C discharge rate. 1C could discharge the battery of all its stored power, if it was full to start off with, in 1 hour. It is sometimes possible to discharge a battery 1200 watt or 100 amp 12 volt battery at twice its C rate, like 2400 watts. This would be considered a 2C discharge. That would theoretically discharge the battery in about 30 minutes. See where I'm going here? So, back to the simple maths. 576 watts for both e-bikes charging would leave us with a surplus of 424 watts for other devices that you might plug into the 230 AC socket simultaneously. However, remember, if you're not generating any external power being sent to your 100 amp hour leisure battery, it will not last a whole lot longer than an hour at a full 1000 or 1C rate of discharge. The pure sine wave inverter usually being the more efficient inverter, but again, you'll probably have to fork out a bit more money for the better, more efficient pure sine wave inverter models. So far, we have figured that we might use 576 watts, so I would look for an inverter that can handle outputting 576 watts or more at a continuous rate, or an even bigger inverter. It'll say continuous rate on the label or what its continuous rate figure is, or in the documentation that comes with the inverter. There is a chance that I might also want to plug in another AC device simultaneously, so I'm going to round off my present inverter requirements to 1000 watts output at 230 volts. Inverter models do tend to come in round numbers, like 500 watt, 1000 watt, 2000 watt, 3000 watt, and so on. That would give me an extra 424 watts that I could use, so plugging in something of 424 watts or less at the same time as the e-bike chargers are being used should work. Now, can my present 100 amp 12 volt DC battery handle the demands that the 1000 watt inverter might put on it? If that is, the full 1000 watts of AC electricity is actually being demanded from the inverter. An easy way to calculate what your leisure battery is capable of dishing out in the way of wattage is to simply calculate the battery output amperage by the nominal battery voltage. This is easy in my case. My battery is 12 volts at 100 amps, or 12 volts at 100 nominal amps. Nominal just being roundabout. It's a term used in the battery world to kind of indicate a rough figure. So 12 times 100 equals 1200. So that works out to be 1200 watts, or 1.2 kW, or 1.2 kilowatts. This being roughly about the maximum wattage I might expect from my 12 volt 100 amp battery. As I stated earlier, 1000 watts AC plus the 10% overhead will equal 1100 watts, or 1100 watts draw from the DC battery. Maybe you didn't notice, but it's pretty much 1000 watts on both sides of the inverter conversion, both on the AC side and the DC side. Only difference being, on the DC side, there is a 10% inverter running overhead that bumps it up to 1100 watts. The wattage stays the same, it's the volts and amps and the electricity type that the inverter converts. So, my example 1000 watt inverter unit will presently work okay for me, as I am probably unlikely to be charging anything a whole lot more than the two e-bikes most of the time, and I have no plans to upgrade my battery or my AC power needs anytime soon. I can even power a 750 watt coffee pod machine, but probably not a 1200 watt induction cooktop. Guess I'll have to cook on gas. If you have any more than one battery, be sure to take into account that difference. For example, if you have two 12 volt 100 amp leisure batteries wired in parallel, please see my number 3 DC electric basics tutorial, the two 100 amp batteries giving you 12 volts at 200 amps when combined. Then you would actually calculate that as a total of 12 times 200 equaling 2400 watts. So you would be able to run a 2000 watt inverter for about an hour, assuming your batteries were fully charged and you were demanding a full 2000 watts from the inverter and nothing else was sucking too much power from your batteries. Again, these figures are based on UK 240 volts. If you're in the USA, you could double these numbers as your voltage is only 110 volts. How do we calculate how long, let's say, a 12 volt 100 amp battery might last? There are so many variables again here that it's almost impossible to calculate exactly, as you may be charging your battery via solar or wind turbine or DC alternator at the same time that you're simultaneously discharging it, or putting what is often termed as a load on it. So we can only use loose approximations. Following my tutorial here, we will give you some idea of what to expect based on many variables. I have always based my figures on a worst case scenario, like I have a 50% charged 12 volt 100 amp lead acid deep cycle leisure battery, and it's a low breeze night, so no wind turbine power and no solar power, and there is presently no alternator running, so we are generating no electricity. There is no electricity being generated in any way to charge the battery. However, we need to have the e-bikes charged up for the following morning, and we need some DC power left over so we have enough power throughout the night to keep the 12 volt DC fridge and the 12 volt lights running. So again, a 1000 watt inverter is as high as I've chosen to go in this, let's say, motorhome scenario. Using the earlier e-bike figures, depending on how fast your e-bike battery charge up, then going by the total wattage as we figured out before for both e-bike batteries being charged up simultaneously, that being a wattage of 576 watts, then you would probably get about a 45-minute charge before completely running your leisure battery right down and your inverter shutting down, as your leisure battery, as I said earlier, is only half full. However, this might still be enough to charge up the e-bike batteries, as they too might not be completely empty, and the e-bike charging blocks are speed chargers. But what I would actually do in this scenario, as it's evening time and there is no sun or wind to generate power, and I have to keep the refrigerator running from the same leisure battery, I would start up my vehicle engine. That is, if you're set up to charge from a combustion engine, split charger or DC to DC type battery charging system, please see my number 6 split charge system tutorial or my number 7 DC to DC charger basics tutorial. And I would charge up the leisure battery via the engine's alternator, whilst the inverter charges up the e-bike battery from the same leisure battery. It would be wise to monitor your battery's usage and its state of charge, that being the amount of electrical power still retained in the battery in this situation. But as I know my alternator charging system creates 20 amps or 240 watts, I would be able to cover the e-bike batteries being charged and still have enough power left in my leisure battery to see me through the night. Hopefully, the following day is sunny enough to finish charging the batteries via my solar panels. Your vehicle motor would just need to tick over, supplementing the inverter's DC power needs, or your battery possibly maybe supplementing your vehicle's DC power generating ability via its alternator. Please see my number 1 vehicle alternator and lead acid battery basics tutorial. Your vehicle engine, you might just run ticking over for 30 to 45 minutes to try and keep the leisure battery at a minimum of a 50% charge, or SOC, or greater. All in all, you should end up with a leisure battery at 50% or more SOC state of charge, and 2 e-bikes fully charged, and maybe even enough power for a coffee pod come breakfast time. If you ever overload the inverter by demanding too much AC power from it, then the inverter will normally warn you by making some kind of alarm or alert sound, and the inverter should then shut down, and you will probably need to reset it, that being when it has adequate voltage again. Many inverters also have fuses built into them. Sometimes these fuses are easily accessible and sometimes not so easy accessed, but all in all, most if not all inverters have safety features built into them so that they are not damaged by being overloaded. But that doesn't mean you shouldn't use fuses on the outside, external fuses. Fuses are there to save not just your life and the device but from the wiring from being overheated and catching fire. On the flip side, inverters often also have a low battery voltage disconnect built in. That means if the inverter senses that the DC battery or batteries that are supplying the inverter with power are getting low in power, then the inverter will automatically shut down before the battery is completely drained. This is often something you can program on your inverter. As I will point out, some batteries when run down beyond a certain percentage are often irreparably damaged. This low voltage disconnect feature in many inverters is, as I said, usually programmable for the varying different battery types, for example lead acid or lithium phosphate or LiFePO4. Please see my tutorials regarding these different battery types. And just one other thing, temperature. Inverters just run better when they are cool. If the ambient temperature is warm, or the weather or environment the inverter is located in is warm, most inverters are generally less efficient and will not necessarily give their full stated wattage. So try to keep your inverter in as cool a place as possible. One of the most important considerations to make and apply when installing an inverter is the gauge or thickness of the electric wiring being used. This is very important, certainly on the DC battery side of the configuration. Please watch my number 5 electric wiring tutorial, as the gauge of thickness and the length of the wire being used to connect the inverter to the battery cannot be stressed anymore as to their importance for both the correct functioning of the inverter and ultimately for safety. Thick gauge wires and the shorter the run of wire to the battery is generally the best setup. On that important note, fuses or electric power breakers. Yet having the appropriately rated fuses or circuit breaker devices on both the DC and AC sides of an inverter are again of absolute tantamount importance. The inverter might have a number of protections built in. However, your wiring, if overloaded, can melt down and can cause a fire. So good quality, appropriate gauge wiring, decent wiring lugs and wiring connections on all the inverter connections and battery connections are of absolute importance. The circuit breaker in my specific case is rated at 200 amps on the heavy gauge battery to inverter cable wire, as my battery is rated at 100 amp. However, it can dish out up to 2C, that being double the rated 100 amp power, as my inverter might have to deal with surges or spikes in AC power demands. That in turn would be converted into surges or spikes on the DC battery side of things. I could actually go up as far as a 240 amp circuit breaker. However, I like personally stay a little lower than my maxed out inverter in the way of cable wire gauge or thickness running from my 100 amp battery to my 1000 watt inverter. I use AWG2 or 35mm2 squared. That is 35 millimeter squared, represented by 35 mm and the number 2 cable wire, which is rated at 260 amps. That being as long as the run of cable wire is less than 6 feet or 2 meters in length. We don't want the wires melting if there is a problem. If I were planning on further increasing the battery amperage in the future by adding another battery or bank of batteries and increasing the wattage factor of the inverter, say up to 2000 watts, then I would use AWG1 or 50 millimeter square cable wire. That again is 50 mm and a little number 2. Or I would double up the AWG2 wire or the 35 millimeter square wire. Again, these figures are based on using less than 6 feet or 2 meters of pure copper thin wall cable wire. Thin wall is the insulating factor, the plastic factor. They call it thin wall, or you can get a thicker, heavier type plastic wall, but thin wall is adequate for our purposes. And I would use a 480 amp breaker. This is on a 2000 watt inverter and a bank of batteries of 200 amps wired up in such a way as they offer 200 amps up. So I would use a 480 amp circuit breaker in between the batteries and inverter with properly cold welded or high compression attached copper lug connectors. They're the connectors that go on the ends of the wires, and you connect them by compressing them. You can get certain special tools, or you could use a vise, and I'll do a whole video on that, although there are a number of videos out there you can watch on compressing copper lugs onto the end of wires. Please see my number 5 electric wiring tutorial. Last thing, just because you are using 12 volt battery power, don't be thinking you can't get an electric shock. The inverter may still retain the capability of giving a nasty, if not fatal, electric shock, even when it's turned off. Protection against an AC electric shock is the job of the leakage current breaker. In my case, with my 1000 watt inverter, I'm in the UK, so I use a 230 volt 10 amp RCCB, which stands for Residual Current Circuit Breaker, with overcurrent and shock protection, installed within a consumer unit housing to reduce electric shocks and keep everything in the AC circuit running safely. In the USA, where most residential appliances run at 110 volts, a voltage leakage current breaker would be referred to as a GFCI, or a ground fault circuit breaker. You can use a single or a dual pole circuit breaker. If you do use a single pole breaker, just be sure to wire it to the live brown cable wire in the UK or the black cable wire in the USA. Sometimes inverter power ratings are measured in VAs. This is a little too complicated for the scope of this tutorial, but VA in short means volts amps and is usually closely related to the calculated wattage figure, if not maybe 5 to 10% over that figure, as it takes into account conversion overheads. VAC means volt alternating current and VDC means volt direct current. I hope this tutorial has given you an idea as to how inverters work and how to calculate the related figures and voltages, amperages and wattages related to inverters. Just remember the correct fuses, and just as important, the correct wiring or gauge of wiring, as the wiring is often the weak point in the chain. One other thing is, if you're buying a cheap Chinese inverter, don't bother using the wire that comes with it. Buy some decent quality copper wire, as the wire that comes thrown in with Chinese inverters tends to be a bit hit or miss. Then again, so are the inverters. But anyway, like and subscribe. Thank you very much.